So thus far, all the acids we've been using have been monoprotic. By that I mean that they only have one acidic hydrogen. However, some acids are polyprotic, which means they have more than one acidic hydrogen. So poly meaning many and protic meaning hydrogens. So here is a short list of some common polyprotic acids. And of these, only sulfuric and phosphoric acids are considered strong. The rest of them are considered to be weak. So we want to take a minute to understand how having more than one acidic hydrogen affects the equilibrium, and of course we want to be able to calculate pHs for a given solution. So we're going to be looking at H2S, which is a diprotic acid. That means it has two hydrogens that can be lost. So in reality what we end up having is two acid equilibriums. So we have Ka1 where the first acidic hydrogen is removed, and so we end up forming hydronium and HS-, but this other hydrogen is also acidic, so we can have a second Ka. So this second hydrogen is lost to form S2-. So we actually have two equilibrium, acidic equilibrium, and we also have two Ka values. So one of the things I want to point out when we have polyprotic acids, typically Ka1 is much larger than Ka2, and this is for a good reason. In the second acidic equilibrium, we are actually removing a hydrogen, H+, away from something that's negatively charged, HS-. So that makes it much more difficult to do. So typically when you have two acid equilibrium, the Ka1 is much larger than the Ka2. So now we want to do some calculations where we find the pH of a polyprotic acid, and we also want to understand some of the other species that are involved in the equilibria. So here we're taking a 0.1 molar solution of H2S, and we are going to calculate the pH. Because Ka1 is so much larger than Ka2, we can assume that the hydronium made in the second acidic step is negligible, so we can ignore that. The amount that's made will not have any effect on the pH that we calculate. So literally we just calculate the concentration of hydronium from the first acidic equilibrium. So just like other weak acid equilibrium, we draw out the Kx equation. H2S plus H2O goes to make hydronium and HS-. We have an initial concentration of 0.1. Some of that's going to dissociate to make X amount of hydronium and X amount of H2S. We then write the equilibrium expression and we plug in these theoretical values, and then we go ahead and assume this X is small and solve for X. So here we insert Ka. We assume X is small, so Ka times 0.1, and then these two combine together to make X squared. If we calculate X, that's going to be equal to our concentration of hydronium and our concentration of HS-, which is 1.0 times 10 to the minus fourth. So even though we have a second acid equilibrium, Ka2, and that second equilibrium is producing more hydronium, we go ahead and assume that the concentration of hydronium that we got from the first acidic step is going to be our equilibrium concentration. The amount that's made in this second step is so small that we can just ignore it. So when we calculate the pH of our 0.1 molar H2S, we just use this concentration of hydronium. So we take the negative log of that, and the pH is 4.0. Also in the question we asked what was the equilibrium concentration of HS-, and the same thing here, we can assume that's being completely made by the first acidic equilibrium. So even though in the second step we are using up some HS-, the amount that's used up is negligible compared to our 1.0 times 10 to the minus fourth. So we can assume our equilibrium concentration of HS- is 1.0 times 10 to the minus fourth. However, we also want to calculate the concentration of S2-, and so this gets into a little trick. And we know because of our equilibrium that we cannot have an absolute zero concentration of S2-. So even though we've assumed that our equilibrium concentrations of hydronium and HS- were determined by the first acidic step, we still need to consider that there is a second acidic step and that there must be some concentration of S2 minus. So what we do is we go ahead and write the equilibrium expression for this second Ka reaction, Ka2, products divided by reactants, so water doesn't make it in there. And in the first part of this calculation, we have already calculated what the equilibrium concentration of hydronium in HS minus are. And remember, we've also decided that those numbers are not going to change. So what we're going to do is take our equilibrium expression and actually solve it for S2 minus, and then we're going to plug in our value for Ka2 and then our equilibrium concentrations of HS minus and hydronium. So we got this from the first step. So when we plug these values in, we're able to calculate the equilibrium concentration of S2 minus, and you can see it's quite small. So it's 1.3 times 10 to the minus 13th. So even though it's small, because S2 minus is involved in an equilibrium, there must be some concentration. It cannot be a zero value. And then also remember that the concentrations of HS minus and hydronium were determined completely by the first step.